Here we discuss our last topic in part 2, which is deriving the governing equation of fluid mechanics. So we've derived the differential equation, the Navier-Stokes equation, and of course those have to be solved subject to certain boundary conditions. So that's what we are discussing now. We're discussing what are the appropriate boundary conditions to impose in fluid mechanics. And so mainly I will split this discussion in two: boundary conditions which are directly imposed onto the velocity, the flow velocity, and boundary conditions which are stress boundary conditions at an interface, for example. And so we'll start with a boundary condition on the velocity. And so there are two places where you can impose a boundary condition of velocity. The first one is very far away from any interface at infinity. This is what we called a Farfield boundary condition. So if we take the example we had before on for an external flow, so say this is our airfoil, a Farfield boundary condition for the velocity would be one that you write at a position far away from any profile. So when x goes to infinity, it could be an unsteady condition. Oftentimes it will be steady. And so when you specify the velocity at infinity, let's say, for example, that you say that it is a constant vector along the x direction, then you impose a Farfield boundary condition. So here, this boundary condition here, sorry, corresponds to saying that very far away from our profile, we have a uniform incoming velocity field in the direction, in the x direction. Okay, and so then there is another place where you can impose a boundary condition of velocity, and that is a boundary condition at an interface. So here we have an interface between two fluids, or between a fluid and a solid. So here is our interface. We could have, for instance, on the top here a fluid, and on the bottom here, there we could have either a fluid or a solid, right? And so here in the fluids region, we would have a certain velocity field that could be u1. It is a field, so it is dependent on location and time, right? Oftentimes I forget to write that, but it is a field. And in the second region, we also have a different velocity field. If you think of it as a solid or as a fluid, you would have a velocity field. And so there are two boundary conditions at an interface that you can impose on the velocity, and one is in the normal direction and one is in the tangential direction. So we'll start with the normal direction. So that means that here we have this ds is a differential element of surface, and here we have a normal vector n, and we are looking for a velocity boundary condition at this interface in the normal direction. And this boundary condition is called the no penetration boundary condition. So this boundary condition is actually is based on the same physical principle of mass conservation that we discussed for when we derived the continuity equation. So this no penetration boundary condition is essentially a statement of mass conservation at an interface. And it simply states the following: imagine you have a fluid here, and you have a solid here, it states that you cannot have a volumetric flow rate of the fluid inside of the solid. Or if you had two fluids that were immiscible, two immiscible fluids are like water and oil would be two immiscible fluids. That means that they cannot mix. And then the statement of mass conservation would mean that there cannot be a volumetric flow rate of water, for instance, into the oil phase, or there cannot be a volumetric flow rate of the oil phase into the water. And how can you do that? Well, you simply write that the volumetric flow rate have to be equal at the interface. So you have to write that the velocity 1, the velocity in phase 1 at the interface, so here we'll take x at the interface, projected onto the normal unit vector here. If I added this ds, that would be the volumetric flow rate of phase 1 through ds, through ds. Has to be equal to the volumetric flow rate of the phase 2, right? And of course I don't have to write this ds here, so this is your no penetration boundary condition. It has a very simple interpretation. It just means that the velocity projected onto the normal vector has to be the same in u1 that it is in u2. So both u1 and u2 essentially follow the interface. If u2 was a solid, then if this second phase here was a solid, then that would be simply the velocity of the solid interface. So this is the first boundary condition, which is in the normal direction, and then there is another, so it's physical again, and it is a statement of mass conservation, and there is a second boundary condition which you can impose in the tangential direction, and that is called the no-slip boundary condition. So here we have the same interface, and now we're going to impose a boundary condition in the tangential direction. So it could be in this direction, have two tangential vector, and then in this direction. So in any direction tangent to your normal vector, so which remains inside the interface, you can impose the no-slip boundary condition. Now the no-slip boundary condition is not based on first principle, is not based on mass conservation. It is more a phenomenological boundary condition. It is something which is often assumed, and I'll go further when you can assume that, and in practice it works well. And essentially the idea behind that, you can read more in the book, is that the velocity field inside of a continuum is continuous. So you don't expect jumps in velocity. I don't expect that my velocity might be like this at a certain location, and then right underneath that you have a jump in velocity that it would take a different value. So within a continuum, the velocity fields are continuous, and in a way, when you cross an interface, you would think that there is no way if you go from a fluid 1 to a fluid 2, there is no way the fluid which is on top of another fluid knows that what is on the bottom, what is underneath, is not of the same fluid, and therefore you expect that the tangential component of the velocity also would be constant. That would be at a fluid-fluid interface, and in that case what you would have is that the tangential component of the velocity field at the interface, so here if I'm in phase 1, if I'm coming to the interface in the first phase, so here I'm in phase 1 and I'm looking at the velocity right on top of the interface, so I'm still in fluid 1, and I look at the projection of this velocity onto a direction tangent to the normal, so inside the interface, this velocity projected onto the t vector, onto the tangential vector, should be the same as the velocity of the fluid which is right underneath the interface. That here would be a no-slip bounding condition at a fluid-fluid interface, for example, with fluid 1 is water again, and fluid 2 is oil. Now, by extension, one may say, well, what happens if my phase 2 is not oil, but let's say what is it if it's a solid, right? Then you have a fluid phase and a solid phase But then the idea goes as follows. Again, the fluid in one doesn't know really that it's not another liquid, but that it's a solid which is underneath, and therefore you would also apply that phenomenologically at a fluid-solid interface. And that is to say then that at a fluid-solid interface, the velocity in the fluid phase projected tangent to the interface is equal to the velocity in the solid phase projected onto a tangent vector. Okay, now you see directly that if my phase 2 was a solid, so if this was a solid and the solid was at rest, so if the velocity of the solid is equal to 0, then you would have that the tangential velocity from the no-slip boundary condition, the tangential velocity at the interface would be equal to 0. This is why it's called a no-slip. You don't have slip between the velocity in this phase and the velocity on the bottom phase. For this boundary condition, for you to be able to apply this boundary condition, you need to assume inside of a fluid a mechanism that allows for friction, that allows a phase to slow down another phase, right? So if I have a solid here which is not moving and I have flow on top, right, then here there needs to be a mechanism that sort of slows down the flow close to the interface to bring it to 0. And so only mathematically, only when you assume that the flow, no, well, not assume, only when you take into account the effect of viscosity inside of a flow can you impose the no-slip boundary condition. So I'm going to add that here. If I go back to the no penetration boundary condition, which we discussed before, it derives from a statement of mass conservation at an interface, and therefore this one is always, you can always imply it, impose it. So you impose it whether you assume the fluid to be inviscid. So when you assume the flow to be inviscid, meaning you neglect the effects of viscosity, then you impose the no penetration boundary condition, and you also assume it when you do take into account the effect of viscosity. So even if you take into account viscosity, so for viscous flows, you also impose the no penetration boundary condition. Okay. However, for the no slip boundary condition, this one, if you assume the flow to be inviscid, you cannot impose the no-slip boundary condition. Right? If you assume that there are no effects of viscosity, then the flow can move at a finite velocity right on top of an interface. It doesn't have to be equal to 0. So for an inviscid flow, I could have a solid interface and right on top have a non-zero velocity inside of the flow. Okay, so you do not impose the no-slip for an inviscid flow. So the no-slip boundary condition is not imposed for inviscid flows, but it is imposed if the flow is viscous. So when the effect of viscosity are taken into account. So when effect of viscosity are taken into account. Okay, one last boundary condition velocity which I want to mention here is one that we have derived before, and that is related to the first boundary condition we imposed, the no penetration boundary condition, but on a deformable interface, and that is the kinematic boundary condition. I think we discussed that in lecture 4. And so the kinematic boundary condition is a statement of mass conservation, and so on the velocity, it relates the velocity of an interface to the flow velocity, and it was simply written partial h partial t plus u, the velocity at the interface, times partial h partial x, plus v, the velocity at the interface, partial h partial y, is equal to the velocity in the z direction, so w at the interface.